Okay, so we've looked at rates of change. We're going to look now at related rates of change. So I suppose the clues in the name. Related rates of change are when we are kind of tying together different rates of change. And a lot of the time, this is going to be to find a rate of change with respect to time. A lot of the time, it's to find it with respect to time. And we kind of use this idea of our chain rule here. So you can see I have it drawn here at the very top, or written out here at the very top. So we're using this idea of a chain rule in that if this is the rate that we want, then if we can set up a chain rule in a specific way so that we have these two rates here that are the same on the bottom of one of our rates and the top of one of our rates, but that's maybe the aspect we don't want to include, then we can use that to find a rate that's going to match up with the one that we do want. So a lot of this is going to be labeling out or listing out the rates that we do have and then being able to relate them and set them up in such a way that we can kind of use them to find the rate that we want, the rate that we're looking for. So what I've said is that these questions require us to use rates that are in the question, but also different rates that we might know of already. So if we follow the steps here, we're drawing a diagram. Okay, we said this in the last part as well. Drawing a diagram is always helpful. Okay, I feel like it's never detrimental to draw a diagram. Then identify the required rate of change. So what are you looking for? What's the question? What do you want? Okay, find and identify the rate given in the question, writing it in the form dy dx. So there usually will be a rate you're looking for and a rate that you're given in the question. So we need to find that rate that we're given in the question as well as the rate that we're looking for. Then we're going to set up the chain rule, lining up the derivatives correctly. So setting up the derivatives in such a way that we're going to kind of cancel out those d parts that we don't want and enable us to have the ones that we do want, to see what missing link is, and we're going to use any other formula we might have. So in a lot of these questions you're working with kind of volume, area, things like that, and you have a lot of formula for those. So you need to be able to pull from those formulas to find rates based on what you need in the question. The question won't always lead you through all of that, so you need to be able to pull it in some in some regards by yourself. And then we use those rates to complete our chain rule. Okay, so we'll jump into an example. We'll have a look at how this kind of all plays out, I suppose, and then we'll kind of go from there a little bit. So a spherical balloon, okay, is being inflated so that its volume is increasing at a constant rate of 24 centimeters cubed per second. Find the rate of increase of the radius when the radius is 10 centimeters. So let's break down important information here. What am I looking for? Find rate of increase of the radius when the radius is 30 centimeters. Now, this comes back to what we were saying in the related rate of change section, or the rates of change section, excuse me. Rate of increase of the radius is going to be dr dt. So that's what I'm looking for. Other points of information that are important. Spherical balloon. Volume is increasing, rate of 24 centimeters per second. Okay, that's dv dt. I want dr dt. So setting all this up, I want to have dr dt. So I need to have two different rates set up in such a way that I have dt on the bottom here and dr on the top here. Okay, because that's going to match up then with what I want to have here. So I need to identify two other parts I can put in. I'm told dv dt in the question, so that suggests to me that here I need to have d or dv. I need to have d or dv. Okay. So to get that, we need to make use of the shape that I have, and it's a spherical balloon, and the volume of a sphere is 4 over 3 pi r cubed. So if I use that to find dv dr, I get 4 pi r squared. Now you might be saying, why are we finding dv dr? Well, one of our nice little tricks that we have for these differentiation questions and these rates of change is that dr dv, to find dr dv, I simply flip the two fractions upside down. So it would make sense that dv dr is dr dv upside down, and it actually does hold mathematically. So we can flip that second part upside down, writing it as a fraction with the 1 over 4 pi r squared on the bottom. So now we can use that in our question here. So if this is my pink part, this is going to be this rate here, and I have my dv dt from before. So d or dv is 1 over 4 pi r squared, and I'm multiplying by dv dt, which is given in the question being 24. So that's going to be 6 over pi r squared, and I was asked when the radius was 30 centimeters. So let's sub that in then. So dv dt at a rate of 30, or d or dt, sorry, 6 over pi times 30 squared, and subbing that into my calculator, and I could leave it in terms of pi as well. 6 over 30 squared is 1 over 150. So 1 over 150 pi centimeters per second. Okay, the s minus 1 is the same as per second. Okay, relating your indice rules there. So that's the general idea that we're following for all of these questions here. Let's look at another example. Oil is dripping onto a surface at a rate of pi over 10 centimeters cubed per second and forms a circular film which may be considered to have a uniform depth of 0.1 centimeters. Find the rate at which the radius of the circular film is increasing when the radius is 5 centimeters. Okay, rate at which the radius is increasing, same as the last question, we're looking for d or dt. So to find d or dt, I need to make use of two different formula, and I need to have d or up here, and I need to have dt there. Okay, we're told oil is dripping onto the surface at a rate of pi over 10 centimeters cubed per second. That is actually, if we think about what's happening here, I have a circular thing and oil is kind of dripping down onto that, okay, and it's building up. Okay, so obviously the oil that I'm getting is presumably building. So that's actually the rate at which the volume of this shape is going to be increasing. That's actually dv dt. The other thing that tells me that volume is measured in centimeters cubed, time obviously in seconds. So I have dv dt up here. The other thing I can use is the shape. If I'm forming a circular film with a depth of 0.1 centimeters, that's going to be a cylinder. Okay, and the volume of a cylinder is pi r squared h. So the rate of change of this volume with respect to the radius is going to be 2, and I know here as well what h is, so 2 pi r h, and I know that h is 0.1, so that's going to be 0.2 pi r, 0.2 pi r. Okay, 0.2 pi. So making use of that then, d or dv would be 1 over 0.2 pi r, and we might be able to use our calculator there to simplify that a little bit, which just gives me 5. So 5 over pi r, 5 over pi. Okay, so I now have d or dv, and I have dv dt, so 5 over pi r multiplied by pi over 10 is going to give me a value of 1 over 2 or 1 over 2 or, and I want to know when or is 5, so that's 1 over 10 centimeters per second. 1 over 10 centimeters per second. Okay, same idea as the last one really. Again, just the shape may be different this time. So let's get into the exam questions here. Then we're starting with the sugar cube from 2021's paper. So a sugar cube is put into coffee. The sugar keeps its cube shape as it dissolves. Okay, the fact that it's a cube stands out to me. Let's write down what I might know. I know the volume of a cube is just length by width by height, or x cubed. As the sugar cube dissolves, its volume decreases at a constant rate. Okay, the volume decreases at a constant rate. So this is the rate of change of the volume. I'm also going to make a note here as well that the volume is decreasing. And what that means for my rate is that my rate is going to be negative. So the rate of change of my volume with respect to time is it's actually decreasing at a rate of 1 over 20. What I'm asked to find here is find the rate of change of xt when the volume reaches a certain value. So I'm trying to find dx dt for v equal to 1 over 64. So the rate of change of the side when the volume reaches a certain value. Now I'm not given a function for the side length at a particular time, so I'm going to have to use a related rate of change here. So let's lay this out. This is what I want to have. So I need to have dt here and I need to have dx here. Looking at the information I have available to me, I can find dv dt and I could find dx dv as well. So let's make note of everything here. So the volume of my cube would be x cubed, so dv dx would be 3x squared. dv dt we already know is minus 1 over 20. And making sure we take that negative there. Using here dx dv, then using the same rule that we've been using a few times now, becomes 1 over 3x squared. So subbing those back into this kind of chain rule here, this related rate part, 1 over 20 gives me minus 1 over 60x squared. Minus 1 over 60x squared. I was asked to find it when the volume of the cube reaches 1 over 64. So if my volume, which is x cubed, is 1 over 64, okay, so if my volume is 1 over 64, then I need to work out what is the side that would give me that volume. So I can take the cubed root of the 64 here and I get 1 over 4. So the side length is actually just a quarter, or 0.25. Okay, so taking that and subbing it all into my rate of change here, it's 1 over 60 by a quarter squared, which is, let's sort that one out, minus 1 over 60 by a quarter squared, which is going to be minus 4 over 15 centimeters per second. Okay, centimeters per second. Now we can see there the rate at which the length of the side, because remember x was the length of the side, so that rate at which it's changing is a negative rate here, as we can see with the minus there. And that kind of does check out with the context of the question, because if we're looking at a sugar cube, the sugar cube, as we dissolve it in the coffee, of course the length of the sides should be getting smaller, so we would expect the rate to be decreasing. So there's a good point there, I suppose, in kind of making sure, is the rate or does the rate make sense? And it does in this case, but always worth asking yourself at the end. Now, if I look back at the context of the question, does the rate that I've gotten make sense? Is it within a reasonable range? Is it the correct sign? Things like that. Looking now at a question from last year's paper, again, it was just kind of a last part of a question. So we have two diagrams here showing a square-based pyramid with the base sides of length c units. The base of the pyramid is horizontal and its perpendicular height is h units. Diagram B shows the same pyramid. It has a horizontal square within the pyramid, a distance of x units from the top of the pyramid. The area of the shaded square is given as such, and x starts to increase at a rate of 3 units per second. This causes s of x to increase as well. Find the rate of change of s of x with respect to time. So as I say, sometimes they will lay it out for us. So we are looking for ds dt. So looking at what I'm given in the question here, I'm told x starts to increase at a rate of 3 units per second. So I'm told dx dt is equal to 3. So that presumably is going to be important for me here. So looking at, if I lay out my chain rule idea here, I know I need to have dt here and ds here. I know I have dx dt, so that tells me that here I need to have ds dx. And I do have the function s here, so I could use that to find dx ds, or ds dx. So I have everything I need. So let's find ds dx here first of all. So to do that, I'm going to start by rearranging my function s, because there's a lot of letters going on with it. So I'm just going to rearrange it slightly, just taking the x squared out to one side. Okay, just taking the x squared out to one side, just to make it a little bit nicer looking for when I go to differentiate it. So ds dx, multiply by the power, reduce the power by 1. 2xc squared over h squared is my rate of change there. So now taking from the related rate that we've set up here, I'm going to take that and I'm going to sub in those values. So subbing in for ds dx and subbing in for dx dt as 3. And I get a value of 6c squared x over h squared, we wanted to find the rate at which it was changing at the instant when x is half the perpendicular height of the pyramid. So if the perpendicular height is h, they're saying here that this is the time at which x is equal to h over 2. X equals h over 2, or a half h. So we're going to have to substitute this now into this formula here and see where that leaves everything, I suppose. So sorting this out here, it's 3c squared h over h squared, which is going to be 3c squared over h. So overall, my derivative, the rate at which x is changing when x is half the perpendicular height, is going to be 3c squared over h. Okay, so again, a lot going on with that question in terms of it's quite a long question written out, but breaking it down, they actually gave you a lot of the information really in the question already. So there wasn't as much for you to have to maybe come up with compared to some of the other questions. Okay, so let's look at the last exam question here, I suppose. So air is pumped into a spherical exercise ball at a rate of 250 centimeters cubed per second. Find the rate at which the radius is increasing when the radius of the ball is 20 centimeters. Give your answer in terms of pi. Breaking down what we have here. So a spherical exercise ball, the usual story, okay, that's a sphere. So the volume of the sphere is 4 over 3 pi r cubed. So we could use that to find dv dr then as 4 pi r squared. We've seen that one a few times, so that's nothing really new to us here. The air is pumped into it at a rate of this, so the rate at which the volume is changing is 250 centimeters cubed per second. To find the rate at which the radius is increasing, we're looking for dr dt, and to find that I'm going to have to use dr dv times dv dt. So making use of what I have here, that's 1 over 4 pi r squared times 250. So 250 over 4 pi r squared, and I wanted when the radius is 20 centimeters, so r is 20, so that's 250 times 4 pi 20 squared. So putting that all together, 20 squared times 4, 1600, so 250 over 1600 pi gives me an answer of 5 over 32 pi. 5 over 32 pi meters per second. 5 over 32 pi meters per second, or centimeters per second even. Find the rate at which the surface area of the ball is increasing when the radius is 20 centimeters. So the surface area of a sphere is 4 pi r squared. The surface area of a sphere is 4 pi r squared. I want to find dA dt. So to use that, I might make use of dA dr and times dr dt. Okay, so I need to find dA dr first. That's going to be 8 pi r. So 8 pi r, and the radius is increasing at a rate of, well, we know from the last part, 5 over 32 pi. Okay, that's our answer from the previous part. So that's going to be 5 over 4 or centimeters. And I need to sub in the 20 centimeters there again. Okay, so let's just kind of really, I suppose, double down on that one. So the reason I'm free to take this exact answer from the end here is that I'm asked to find the rate at which the surface area is increasing when the radius is 20, which is the same radius I had used at this part. Otherwise, we might have to go back to this part here and see what the radius was in that sort of section, okay? But for this case, we're free to just take the exact kind of answer that we had from the previous part, I suppose. I'll just take it kind of from that respect, I suppose. So we know dr dt from the radius with respect to time, and we're subbing in that value of 20 there. So, 5 over 32 pi. So that's going to give me 5 over 4, or I need to sub in or equal to 20. So 5 times 20 over 4, which is going to give me 25 centimeters squared per second. That's my rate of change there, rate of increase. Okay, and that's really the end of that question. Okay, so the key thing with this whole section really of these related rates is just being able to tie together the different questions and the different rates and the different formula that you have within those questions. Okay, so as we saw, like, they don't always give you all the information that you need. You might not always have every single formula that you need. You might need to go looking. A lot of the time it is shapes, it is particular kind of shapes or volumes or things that we're using in that respect. So you will be able to, or you should have those formulas in your log tables or in your formula tables book. So it's not that you need to know the formulas off, but you have to know to go to look for them. And then just being able to tie together the formulas in the correct way to give you the answer that you want to. So it's kind of managing all of those things. It can look fairly simple, and then for that reason I suppose sometimes the questions can be a little bit harder. It's just making sure as well that, like, you're fit for maybe where this isn't a full question, where it comes up as part of a question, where it ties into other parts, and kind of all of that building on top of each other. But I suppose the key aspect is really this idea here at the start, being able to lay out what you're looking for, fill in the blanks then to see what the other rates that you're going to be using are, and being able to identify the rate then that you have in the question as well.